In the fourth end, a mistake from Sweden left an opening.
The very beginning of curling may just be my favorite. You'll see here that the curler starts in a bit of a lunge position, really just working those glutes. Then goes forward, pushing the stone. This force from the push actually has a very interesting name, the force of push. This force of push creates an unbalanced horizontal force, and the stone accelerates in that direction until the force stops when the curler lets go.
Canada to go back in front. Swedish fourth Pritz's attempted takeout shot only did half its job.
Alright, now this is the real interesting bit of the game. In the photo here, you can see the stone sliding down the run at a constant speed. Just a nice, real constant, not changing speed. But again, you might find yourself pondering the question, why? Well, the first part has to do with that vertically, it does not accelerate. This is because the normal force and the force of gravity are equal, just like you will see in a later example. Since the rock is going on the ice, we can assume that there is no friction between the rock and the ice. Since then there are no forces acting on it horizontally, it was in motion and will continue to move at a constant speed down the track, just real nice and constant.
A yellow Canadian stone clinging on at the edge.
A curling stone, stone A, moves forward and hits another curling stone, stone B. What an upset. As you see here, a crazy thing just happened. Stone A bumped into stone B. Let's get in close to see exactly what happened when this event occurred. Stone A and stone B collide, creating the force of stone A on B and the force of stone B on A. These two are third law pairs. The force of stone A on B causes stone B to accelerate, making it move away from stone A, and the force of stone B on A causes stone A to accelerate. However, since it is in motion, this acceleration in the opposite direction it was moving caused it to slow down.
Canada scored 2 from the end to go 3.
Here we see the stone sitting at the end of the run. It appears still. But why? The answer is quite simple, actually. There's only one thing touching the stone: the ground. The ground creates an upward normal force equal to the force of gravity, so there is no vertical acceleration. Since nothing else is touching the stone, there are no other forces acting on it, and there is no horizontal acceleration either, so the stone is still.
1 in front.
But how much force does a curler use? Well, let me show you. The average curling stone mass is 20 kilograms. The average time is 1.75 seconds. And the final velocity is 2 meters per second. We then plug this information into our handy-dandy velocity equation to find the acceleration. Once the acceleration has been found, we plug that into the acceleration equation for Newton's second law. And boom. We have the force of our curler, which is 22.856. And that's not so bad, is it? Thank you.
Yo, man, let's get out of here. Word to your mother.